Well, thank you very much. It's a real pleasure and an honor to be here. I'm representing Transphorm today. It's a company here in Goleta, and we're pretty excited about what we're doing, and I hope we can convince you that what we're doing is actually useful. So our tagline is Reimagine Power Conversion. Power conversion is a process that has been happening since electrical energy was discovered. Reimagine means we are converting what is considered to be a staid and well-developed industrial sector. We're trying to sexy it up a little bit. What happened? Something happened, boss. You'll have to, yeah, that's great. Thank you very much. So, introduction to Transphorm. What do? We basically convert energy from one form to another. This is required for any electrical energy appliance. I call it an appliance. A supercomputer is an appliance. A washing machine is an appliance. So any electrical energy function will require us to do these things: convert either AC to DC, AC from the outlet, DC to the laptop, for example. DC to AC, this is an inverter application. Say this could be a photovoltaic panel, this could be power to the grid, this could be a DC battery pack in a Tesla or a Prius, and this could be AC to the motor that drives the car. DC to DC power conversion happens all the time. This happens also in a car where you take a battery pack and raise the voltage to another value. These conversions happen everywhere. It's ubiquitous, and the inefficiencies of conversion are hundreds of terawatt hours. Okay, and what we're trying to do, Transphorm, we believe, is the first company to address this at a platform level, and I'll explain what I mean by that. This is a little bit of bragging. It's an old slide. But basically, the most important thing is that we have money to do this stuff. Okay, we've been funded by good VC firms like Kleiner Perkins Foundation, Lux, and Google Ventures. We raised about $38 million. We got voted as one of the best in clean tech startups in 2011. That's for you to judge, though. So the point that I try to make is that we are paying a hidden tax on electricity. It shouldn't be off. It should be on electricity. And if you look at the way electricity is generated in the US, there's so much in coal, over 50% in coal, natural gas, nuclear, hydro, wind, as Jim just talked about. And I'm still kind of in shock after his presentation. It's hard to follow him. But at the end of the day, of all the generation that occurs, over 10% of the electrical energy that is generated in the US is lost in conversion. This is about $40 billion of tax that we are paying, not knowing that we're paying it. That's about 318 coal power plant equivalents of energy that is just lost in conversion. I'm not talking about lost on the grid and stuff like that. This is lost in places like this, you know, the brick that you carry around in your laptop. Okay, so the important thing is, and I'm not trying to make a point of this other than making a point of it, is that the amount that we can save in electrical energy by eliminating these losses is more than all the renewables combined today. Okay, I want renewables to go up. I hope the statement is no longer fact in a few years, but it's a fact today. So want watts, waste not. Okay, so how much is a terawatt hour? So for example, San Francisco uses 6 terawatt hours of energy, all right? New York City is about 50 terawatt hours, and New York City and the suburbs, and Vegas is about 33 terawatt hours of energy, okay? So you can look at all this energy in the world, in the US, and the West Coast, all of the West Coast consumes about 270 terawatt hours of energy. The amount of conversion losses that occur today, and I'm saying Transphorm saving potential, assuming we get 100% of the market. Of course we won't. But all the players in this space of electrical energy conversion efficiencies can save over 300 terawatt hours. This is equivalent basically to taking the West Coast off the grid, I mean, figuratively speaking. But basically, that's the amount of impact you have, which is enormous. Now, I'll give you a couple of real-life examples. First of all, you know, you've got to make money doing this stuff. You know, and subsidies are nice, and policy is really important. But if you can do it at least partway by making money, that'll be good. And the way you make money is either by amortizing energy efficiency cost, which means you tell the customer, hey, pay up now and, over the life cycle, you will get back what you pay now. That's a good proposition. The other is if you can provide value in form in addition to function. All right. I mean, the kind of stuff that Apple does so well, for example, right? So if I told you that, look, I can take this brick that you carry around today and I can just make it vanish with my technology, you would pay a little money for it, more than the electrical energy savings that you produce. But the reason you can make it vanish is because you have made it efficient and you don't need to put the heat sink that makes it so big. So what ends up happening is at Transphorm are looking at places where the form plus function gives you the value. Another example is inside a hybrid vehicle. This is a Prius. And the nice thing about a Prius is that you have both a battery and an internal combustion engine, which the nice thing about it, it highlights the point I'm trying to make. You have two radiators in a Prius. Again, I'm going back to form plus function. So here's an internal combustion engine, and so you have your normal radiator cooling the internal combustion engine, but obviously that coolant is relatively warm. And then, in addition to that internal combustion engine, you have a second radiator. So a Prius comes with two radiators, right? Buy one, get one free kind of thing. And this one is the one that cools the power, but it's not quite free. That's the problem. This active cooling is for the electronics, this power unit that actually converts the battery power to the power that goes into the drivetrain. So we have two radiators. And the reason is you can't use the hot coolant to cool the electronics, right? So what we are trying to do at Transphorm is to basically affect this electrical power handling unit so that it doesn't need active liquid cooling. Okay, if we can do that, if you can make it by increased efficiency, then the most important thing is that the electronics radiator is removed. I agree with what J.B. Straubel said before, that it's not only the efficiency. If you do power electronics enhancements in efficiency, yeah, that's nice, but it's really the battery that matters. I agree. However, if you can get rid of the liquid cooling, you change the game, because there is nothing more valuable in a car than the space under the hood. Okay. If I told an engineer that I'm going to give you 11.2 liters of space, which is what a Toyota Prius uses, 11.2 liters of space, most of it is cooling, and I give you 11.2 liters of space, the guy's going to kiss you on the cheek. Right? So that's form plus function. So that's what we're trying to do. So what are the markets we operate in? We operate in really old school markets, okay? Industrial motor drives. This is as old school as it gets. But 50% of the electrical energy consumed in the US is used to move things, all right? Escalators, washing machines, you name it. So, and that's basically the following conversion. You take 230 volts of AC out, you go through a DC conversion and then go back to AC, all right? So you go AC, DC, AC. And in that conversion, there are losses of about 207 terawatt hours. Data server power supplies, this thing is going gangbusters right now. I mean, this is the power hog, which is increasing like crazy because of the web is, there's no end to it. And here, the power supply of the server, not the server itself. We can't do anything about that. That's more like John Bowser's gig, I mean, he can do these interconnects that can make the server get better. I don't do that. What we do is we do the power supply part of it. And there you can make these kinds of efficiency enhancements. As you can see, solar inverters, this is a very big deal. Solar inverters is going through architectural evolutions. Are we going to use a central inverter? Are we going to use a micro inverter, an inverter behind each panel? Are we going to use something in between? These architectures are developing, and as the architectures develop, the solutions will develop with them. But what you need is basically something that can plug into whatever be the architect's choice at the end. Electric motor inverter is basically 202 volts DC, and you step it up to 650 volts AC, and then you drive your 600 volts DC, that should be, then you drive your AC motor with it. So you can see where all these things happen. The markets are important, as was mentioned. You really got to look at markets. At the end, you have to be in a business. The markets are, and this is a conservative estimate. That is, I'm assuming that I'm going to only enter certain parts of this market that my technology, Transphorm's technology, can address. And there's $1 billion markets in almost each of these segments, in motor control, solar, data power, center power supplies, and there are more markets as well. Hybrid cars and in EV inverters, that market is small now, growing very fast. Okay, 5 minutes, I better move. So how do we do this? We use gallium nitride. It's the same material that is used for solid-state lighting. And gallium nitride, I won't go through the material properties. I'll just tell you that bigger is better in this case, all right? And gallium nitride is bigger than silicon and more, and can hold much better, can convert power more efficiently. There's a difference in the Moore's law. We also have a Moore's law in the power electronics industry, and it's different from scaling Moore's law. What we value most is output power density. That means how much power can you convert per centimeter cube. And you can only do this if you're more efficient, because if you're inefficient, you can't convert power in a small volume because the damn thing's going to melt. So here what happens is it's a relay. The race is a relay race where you hand over from technology to technology, a bipolar transistor to an IGBT, and it's plateaued now. And now what is happening is that the device of choice is going to go into a different material, and we believe it's gallium nitride. Okay? So that baton is going to get handed over to Transphorm's GaN, everybody else's GaN, obviously. The nice thing about it is that we can get lots of breakdown voltage. You can see that we can get up to 2,000 volts. 600 volts is used in data server power supplies. 1,200 volts is used in electric vehicles, for example, and motor drives. 2,000 volts and larger is used in grid applications. All I want to say is that we can scale to large voltages. What do we do as a company? As a company, we decided that we are going to address everything, right from the material growth. This is all done in Goleta, in our company on Castilian. Gallium nitride technology, we have a fab, we make our chips, we make the circuits, we make the modules. And the reason is, in these new technologies, you can't just make something and hand it over to the customer and says, the problem is yours. What you have to do is, you've got to make sure that you can respond to customers at the appropriate pain point, because I will guarantee you, the first thing, and I can guarantee because this happened to us, you give it to the guy and he says, the thing blew up on me, all right? And so why did it blow up? We don't know unless, is it the material failing, is it the device failing, or the circuit itself failed? If you don't know all of this, you can't respond to the customer. We've done that. I'll give you a couple of examples. We just announced diode and transistor products. This is what is called a boost circuit. It doesn't really matter. What really matters is that it is 99% efficient, okay? So, which means I can convert from 200 volts to 400 volts with 99.2% efficiency. This is a big deal. And it tells you that Transphorm's technology is starting in these little pockets, but will go. And it's not only us. I'm using Transphorm because I represent Transphorm. It's going to be a multi-industry, huge new set of players. I just want to make one statement. It's not good enough to have a technology that is is basically, we cannot be a one-string band. You've got to have any technology in this expensive space can only win if it can provide multiple solutions, or economies of scale can be applied. And it should not be too disruptive. You can't make something so sexy that people can't use it. Right? So what we want to do is that we focused on, okay, this is a hard technology to use, let's make it simple for the consumer, and make sure that it has lots of applications. So thanks to Shuji Nakamura, Jim, and Steve, and all these guys who've really pioneered lighting so much, we have a $7 billion market in lighting, and it's growing. You need employees. That's where UCSB is so amazing. We train all these guys, and they're plug and play, You take them into you get them their PhD, and then boom, they're off and running, and they can lead the world. And this is awesome. Primit, who's the president, is a UCSB alum from 1996, for example. This is the sister market, $7 billion with the same material, gallium nitride, okay? We are very thankful. We cheer them on all the time, because the more successful they are, the cheaper the raw materials are for us. So we are their biggest fans. I'd like to end, because I know that Linda is like squirming in a chair right now. I'd like to end with the following statement that UC Santa Barbara, has been an amazing place, especially for me, and because this is my second startup, the first one worked out well, the second one, I hope, works out even better. Jeff mentioned the new kind of, I don't know what you use something for the new Silicon Valley, Energy Valley or something, and before that, we are in the gallium nitride valley here. It's the new material which has so many implications that we got to just keep developing companies in this area, in Goleta and Santa Barbara. And the philosophy of UC Santa Barbara is great. Do some things right, don't do everything average. Because the problem is, when you do some things right, you get people who are really well-trained, and because the marketplace is about the most brutal thing in the world. And you can't learn too much. I mean, you learn, of course, but you cannot learn too much out there. You have to learn to swim before you jump in. Administration is supportive. The technology transfer office has changed like crazy. It's a much more user-friendly office than it used to be. And the ONR has funded my research, our research in gallium nitride for over 15 years. And the way we started the technology, we started it by licensing all the technology we had developed at UCSB and patented at UCSB. Once with that base patent portfolio, we started inventing beyond that at Transphorm. So I hope that I've left you with an image of UC Santa Barbara is a great place to actually spin out companies. I hope more VCs stop by here. We are way better than Stanford. And we'll keep pushing things out the door here. This is where physical and material sciences, at least, I don't want to, CS and others can speak for themselves, but in my domain, I think it's awesome, and I hope we keep repeating the story over and over again. Thank you.